Chemistry by Timberlake, Section 6.1 on the Octet Rule and ions. The Octet Rule is one of the very first things that I teach you. All elements, all atoms, everything combining with everything else, reacting, interacting with everything else, wants to be energetically stable. And that would be like a rock wanting to fall to the bottom of the hill. If a rock is dislodged and it starts rolling, it will continue falling until it's stable. You might think, oh, it's going to fall to the bottom of the hill. Well, it might not fall to the bottom of the hill. It might find a ledge along the edge of the hill. As long as it's stable, it stops. Okay? If it's not stable, it continues to roll. It's exactly the same thing. It's at a high potential energy and it wants to go all the way to low potential energy. Every chemical is exactly the same. They will react with each other until electrically, meaning electronically, electron-wise, they are at the lowest potential energy stability pattern that they can find. And from the periodic table, the easy answer is that this is the noble gas configuration. The last column on the periodic table, every single one of them that have in common is that they are very, very stable. They don't have even lots of reactions. You don't even have lots of xenon compounds. You only have a handful of noble gas compounds because they're so not reactive that they're even called inert. Inert means don't worry about it. It's not going to react with anything. It's not going to hurt you. It won't blow up. It won't cause anything. It won't rust. It's just inert. It doesn't react. Why? It doesn't need to react. Okay? It's rich and beautiful and it doesn't need no husband. Okay? So too bad for you. So let's look at some of these and why ions is in this chapter, because not only is it that all elements tend towards a configuration equal to noble gas, but many times in order to get there, they're no longer going to be neutral. They're going to give away some electrons or they're going to steal some electrons in order to become like the noble gases. So let's look at some examples. So what's an octet? 8 valence electrons. So if you remember that if you look across the periodic table and you take away the valley, take away the D subshell, you take away the F subshell, what you have left is S. The S subshell has 1 orbital in it. There's 2 girls in that room. Then you're going to have 3 orbitals in the P subshell. There's 6 girls total. So 2 and 8 is 6. Or 2 and 6 are 8. 2 and 6 are 8. So that means the S and P subshells are your valence electrons. And when you have a valence electron equal to 8, that's stability. Okay? So many times, other than helium, helium is stable at 2. Okay? Helium has a noble gas configuration, so it's very stable. And if hydrogen can become like helium, it's very stable. Every other element needs to have a P6. So for instance, neon, 2s2, 2p6, argon, 3s2, 3p6, krypton, 4s2, 4p6. Okay? Now remember, these D's are not counted. These are internal because this is from the third shell. Only these last, the S's and the P, are considered octets. So atoms acquire octets. See, the only thing that is an octet is something that's naturally in group 8. Okay, so if you're krypton or if you're argon or if you're neon, great job for you, you're stable. But if you're anything else, you are not stable and you want to be like argon. You don't want to become argon, you just want to have the same number of electrons as argon. So if you need to steal some in order to be like argon, that's what you do. If you want to share some in order to be like neon or krypton, that's what you do. So in atoms, to become more stable, they lose, gain, or share valence electrons. That is the most important sentence for this entire year. You will learn more about chemistry if I had one sentence That's the most important sentence of the year. In order to be stable, in order to have an octet, in order to be like a noble gas configuration, which is very stable, electrons will either steal, get stolen from, or share electrons in order to gain a noble gas configuration for every element in the compound. Okay? If it loses electrons, now think about it, that would be like me losing a debt. If an electron is negative, it'd be like losing my phone bill. Okay? I have a phone bill, I have to pay this money, somebody comes and pays that phone bill. They steal my bill. Okay? Oh, please let me pay this phone bill for you because you're so awesome. Well, that's the same as if they gave me the money to pay for it. If they took it away from me so that it's no longer a debt, that's exactly the same as if they paid for it by giving me the money and then I paying for it. Either case, I'm richer than I was. So if I lose an electron, I'm positive. I'm a positive ion, and that's called a cation. We'll look at all these in a minute. If I gain an electron, okay, so I gain an electron in order to have an octet, I've stolen a negative. That makes me more negative. If I take that negative upon myself, I have more electrons than I have protons, and my charge is now negative. That is an anion. So cations are positive, anions are negative. And we'll review that in just a minute. Okay? All right, so ionic bonds are a bond between two elements such that by stealing an electron, one becomes negative, and the one I've stolen it from becomes positive. And because that's true, then you're going to end up being an ionic bond, and both of them together will simply stick together like socks in the dryer. Okay, that's an electric charge. If you have a positive and a negative, they electronically attract, and then that attraction is called a bond. All right, but they're no longer neutral, they are an ion. A covalent bond shares electrons so that it would be like me sharing a dollar with you, and according to our economy, I would have a full dollar and you would have a full dollar. That would be a pretty easy way. Okay? I guess it's like sharing computer files. We both end up having it. All right, so ionic is stealing, covalent is sharing. Can you write that in your notes? Pretty important. All right, anything on the left side of the periodic table is going to lose electrons and become positive. Okay, so for instance, if you were to have a sodium is in group 1. Let's say I steal that last electron. All right, I had one in the outer shell. Now I steal that. Do you see that I no longer have an outer shell? My inside shell becomes my outside shell because I took everything in that shell. Right? So I took all the electrons in the shell because it was just one. That means when I take it away, there is no last shell, and the very next inside shell becomes the outside shell. Well, the next inside shell is full. So by stealing an electron off of a group 1, it makes it the same electron configuration as if it were a noble gas in the previous row. Right? If you have a group 2, so there's 2 electrons, and I steal 2 electrons, I make it the same as if it were a noble gas in the previous period. Okay, it's exactly the same. So anything on the left side of the periodic table tends to get stolen from, and they still are stable because when you steal all their valence electrons in that outer shell, the previous shell, which is already full, becomes the outer shell, and now it's stable. But by stealing an electron, it makes it positive. So metals form positive ions. Okay. So here's an example. Here's sodium. Sodium has an outside shell with 1 electron in it. If I steal it away, I now have 11 protons, but only 10 electrons. So I have 1 more proton than I do electrons, And that is where I put it right here, sodium plus. That's a cation, C-A-T, and I see the T in cation as that plus. Cation is a positive ion. Okay. So if it was originally neutral, but I gave away one electron, getting it stolen, I'm now no longer neutral, I'm positive. So when you steal an electron, you increase the positive charge 1. Okay, it goes up by a positive charge every time you steal an electron. So if you steal 1 electron, it'll be a positive 2. A positive 1. If you steal 2 electrons, it's a positive 2. If you steal 3 electrons, it's a positive 3. Here's another example. Here's magnesium. It's in group 2. So if I steal 1, it becomes positive 1, but it's still not stable, because now that just has the configuration of a first column electron, so it's no big deal. If I steal another one, I have made it positive 2, but I have the same configuration as the noble gas in the previous row. So it's very stable, but it's a positive 2. So it's magnesium 2 plus ion, positive. So these are metals. These are on the left side of the periodic table. Okay. So what's the charge? It used to be neutral because I had the same number of protons and neutrons. Every neutral atom adds up to 0. But what if I steal 2 electrons? I now have 10 electrons but 12 protons. That means it's going to be positive. So every negative that you steal, you're going to go up by 1 in a charge. So what is the number of valence electrons of, aluminum, sorry. What's the valence electrons for aluminum? Well, aluminum is in the third column, so there's 3 valence electrons. Okay, so if you steal 3 electrons, aluminum would become positive 3, and aluminum is most of the time positive 3. I think all the time. I don't know of a case it's not. The electron change for the octet. Now here's your 2 choices. Is it more likely for something that has 3 electrons to steal 5 and become 8, or to give away 3 and become 8? Okay, by giving away 3, the last shell is now 0, and the previous shell had 8. So by giving away 3, I'm stable. Or by stealing 5, I'm stable. Do you see it's more likely to happen to get 3 stolen than it is to steal 5? Because these guys are not trying to steal. They're bumping into each other with sufficient energy for that electron to transfer. That's what stealing means. And so if they had to bump into 5 things and steal from them, it's unlikely that that would ever happen. Even if they were to bump for the rest of eternity, you probably wouldn't get lots of things that would steal 5 things. All right. The ionic charge of aluminum, if it was a 3 electrons in the valence shell, is you steal 3, and every one you steal goes up by 1, and so it'll be positive 3. And so the symbol for aluminum ion is Al, positive 3. What a good set of questions. These are excellent. In fact, will you go through this? Even stop the video and write it down. Make sure you can do this, because I really like these questions. All right, if metals on the left become positive, then nonmetals on the right become negative. Okay, so in order for something in group 7 to be like 8, it's going to steal an extra one. If it has 7 and it needs 8, it'll steal 1 more. If you steal an electron, you become negative. And so for every electron you steal, your charge will drop by 1. Okay, so by stealing from group 7, or group 7 steals, it becomes -1. If group 6 steals, group 6 is 2 away from 8, so I need to steal 2 to be like 8. If group 5 steals, 6, 7, 8, I would need to steal 3, so that would be -3. So group 5 would be -3, group 6 would be -2, group 7 would be -1. Okay, we saw that group 1 was +1, group 2 was +2, group 3 was +3. Group 7 is -1, group 6 is -2, see how it's going backwards? Group 5 is -3. So what's going to happen? Here's chlorine. Okay, chlorine is going to steal. It'll steal an electron. It now has 18 electrons. but it only has 17 protons, so it has one extra electron than it does protons, and so you end up with a negative charge. You have more electrons than protons, so it's a negative charge. Originally, chlorine was neutral, but if I have one extra electron, when they cancel each other, I'm going to have a net charge of -1. Okay, so what becomes? I think you can guess these. Anything in group 1, okay, anything in group 1, lithium, sodium, potassium, all become +1. Anything in group 2 become +2. Anything in group 3 usually, especially aluminum and boron, become +3. Now go backwards. I never go to 4. Carbon group really doesn't play this game. It doesn't do the positive negative thing. It can. Most of the time carbon shares. Okay, carbon makes covalent bonds. They share bonds, share electrons. But I always do 1, 2, and 3 and then go backwards. 7 is 1 away from 8, so it steals 1. 6 is 2 away from 8, so it steals 2. And 5 is 3 away from 8, so it steals 3. Okay. So an ion you become an ion by trying to get a noble gas configuration and be stable. But by being an ion, you're no longer neutral. You're either charged positive or if you're charged negative. So this is the review. Metals in group 1 become +1. Metals in group 2 become +2. Metals in group 3 become +3. Now go backwards. Nonmetals in group 7 become -1. Nonmetals in group 6 become -2. Nonmetals in group 5 become -3. Okay, and then you can see that. Group 1s become 1. Group 2 becomes 2. Group 3 becomes 3. Group 7 becomes -1. Group 6 becomes -2. Group 5 becomes -3. Select the correct answer for sulfur. Sulfur is in group 6. Okay, so if it's 2 away from 8, is it going to steal or give away? It only needs 2, so it's going to steal, and it steals 2. And if every one it steals, it goes down by 1 charge. So the group number for sulfur is 6. Okay. I'm sorry, it's 6A or it's 16. It depends. Our periodic table on our wall is 16. The number of valence electrons in sulfur is 6. The change in electrons for an octet means it needs to go from 6 to 8, so it's gaining 2. And the ionic charge for sulfide is 2 negative. Okay, do those and see if that makes sense to you. I hope that makes sense. Okay, and that's all for today. I will see you later.